He is a postdoctoral researcher at the Control Systems Lab of Toyota Technological Institute in Japan. It's an independent institute, but funded by Toyota Motor Company, as I've understood. And he's going to talk about a project investigating the possibility of using large-sized flapping wing flying robots for use in search and rescue operations. His presentation will be focused on the basic design analysis, modeling, and some real experiments of the bird-like flapping wing flying robot.
Okay, thank you, Professor, for the introduction. So to save some time, I will just skip this page completely. So I will first talk about a little bit on what our motivation is so that it helps to explain our approach, although most of this is rather obvious. So we are interested in using a large-size flapping wing flying robots capable of strong flight in outdoor environments. Current research projects going on are using small-sized flapping wing flying robots. So that's why we are thinking of a large-sized. And it should be a real robot capable of using search and rescue operations. Why search and rescue? Because currently people are proposing quadcopters and other robots like a ducted air UAV. This one was actually used in Fukushima, but one of the problems of using such big-sized robots is that they weigh quite a bit. So if they crash, they will directly lead to, they will leave a large crash impact. So this was aired on the Japanese NHK TV, and it shows the ducted air UAV actually flying. And you will see the moment it falls very rapidly because it has failed completely, and it crashes, and it's almost destroyed. So those are the remains. Whereas if you use a flapping wing flying robot, it has got natural gliding capabilities. So even if it were to fail and crash, it will naturally glide down to a softer landing. And besides that, flapping wing flying robots are largely lightweight, and they have no rotors or propellers with which they can inflict injury. And in the future, when the technology has matured and they are properly designed, they should be super maneuverable. So our approach is quite different from current ongoing projects in other universities. Instead of doing things in a design-oriented way, we adopted a more pragmatic approach where we have very practical methods of deducing the thrust and the lift, etc., because we are mostly concerned with autonomous motion control. What we would like to do is to send a flapping wing flying robot flying around a disaster zone, let's say in a circular trajectory or helical trajectory, things like that. So this is the flapping wing flying robot that we are using, and it has been supplied to us by Kazuhiko Kakuta of Japan. I will show you a quick video of the robot in actual flight. So this video was taken by our collaborator, Kazuhiko Kakuta, and so this is the robot in flight. So as you can see, it is quite large. It has got quite a bit of thrust and lift, so it can penetrate some winds and even fly in light rain, and even if there are gusts of winds, it can still fly. And it's quite large. The wingspan of one wing is just 60 centimeters, so altogether it's 1.2 meters, and it has a gross weight of 430 grams, so it will solve some of the problems we have with some of these small robots, where you can only put like batteries that are only so big. And now I will just talk about the low-level hardware design. We have one single brushless model that is used to realize the flapping movements of both the wings. So they both flap concurrently. We have one servo for rudder control and one servo for elevator control. So if we consider the brushless DC model that is used for the flapping wings, we use a slider crank arm mechanism to realize that flapping mechanism. So the brushless motor is connected to the slider crank arm mechanism via some gear trains, and it's used to convert the rotational motion of the motor into the up and down flapping movements. So you have the motor over here. At the back, you have two gears. That's the last gear, and that directly drives the crank arm, and that's the connecting rod and the wing root, which moves up and down. So, because it uses a slider crank arm mechanism, which is actually one of the oldest machines, we can easily model the flapping mechanism. So if the angular velocity of the brushless motor is something, then we know the gear ratio that we are using for speed reduction. So with that, we can find the reduced speed of this gear, the last gear. And that's the gear that actually drives the crank arm mechanism directly. So we can use the physics of a slider crank arm mechanism, and we can use it to estimate the speed with which the slider goes up and down. And those are the equations borrowed directly from the physics of a crank arm mechanism. That's the linear speed with which the wing root moves up and down, and that's the crank angle. And if we have that speed, and if we know the reduced speed of the last gear, then we can very easily find the flapping frequency. For sensors, we are using the APM 2.6, which one of the previous researchers has also presented, and it has got onboard memory. So right now, at this development stage, it is not fully autonomous, but we log the sensor data on the onboard memory, and then later we retrieve the data and we analyze the data. For pitch control, we use this tail as an elevator. When it pitches or when it moves or when it deflects up and down, it creates a moment about the center of gravity. And the moment, the theoretical value of that moment can directly be deduced from fluid dynamics. So this equation is very common. And that's the angular acceleration. And these are the theoretical equations. We can use the sensors to get the data directly. So we can use the gyroscopes to get the pitch angle with which we can get the accelerations. So apart from the pitching that we want, which is caused by this elevator deflection, there is some extra pitching caused by the flapping wings. It's a very large robot, so there is some extra pitching caused. So in the very beginning, when we were doing experiments, when we noticed the sensor data, there were some anomalies which we couldn't understand, because in our experimental setup, the robot was fixed very tightly, so we didn't actually see the pitching. Even if we increase the flapping speed, you still see like a little bit of pitching, but it's not very obvious. But if we remove this solid mechanism, and if we try and fix the robot to just one single point, then you will see how obvious the pitching is. You will see pitches. So that's one anomaly that we also have to model. And we can model that pitching by examining the mechanism that causes the flapping wing, and that is the crank arm mechanism. And for the crank arm mechanism, there is the diagram known as a turning moments diagram, and that diagram is a representation of the moments that are caused, which is a function of the crank angle. So the induced moment is a function of the crank angle, and that is given by this expression. And this initial force is given by a separate expression. So this can be used as a guide to model the extra pitching that is created. And as I have mentioned, the extra moment that is created is a function of the crank angle. And the moment is 0 when the crank angle is at the 0, pi, and 2 pi positions. And it's maximum when the first derivative is maximum or minimum. So the extra moments that are caused is something like this. So if you have the gyro sensor, and if the robot is flying in a straight and level flight, but if you examine the gyro sensor, you will still find some curves like this. So we have to filter that data from the sensor data, and since the moment is periodic over a full crank revolution, and it's continuous, since the wings are flapping continuously, then we can simply rewrite that equation as a Fourier series of a certain frequency. We can expand it, we can find the coefficients, and from the power spectrum, we can find the particular frequency and filter it. The yaw control is by means of the rudder deflection. So again, when the rudder moves from the left or to the right, there is a moment created about the center of gravity. And again, that's the theoretical magnitude of the moment that's created. Now, in the very first model that we had, and from what we have written in the paper, there was no rolling moment caused because the rudder was turning so quickly within a fraction of a second that there was no rolling caused. So there was some induced rolling but no active rolling. But as it is for now, we have changed the servo motor, so the rudder twists and turns more slowly. So there is now some pitching, some rolling caused too. So we will have to consider that in our next model. Now for the dynamical modeling, so we assign 2 coordinate frames, the body frame and the initial frame, and the rest of our mathematical treatment is based on this. Typically, to represent pose, we can use something like this for the position and the orientation, but instead of using Euler angles for the pose or for the orientation, we use quaternions, and I will be explaining the reason for that later on. So we avoid using Euler angles because of the singularities of rotation vectors associated with using Euler angles. There is non-uniqueness of rotation vectors going from one orientation to another. Also, there is the phenomenon known as gimbal lock, where there is a loss of 1 degree of freedom. And also, finally, when we use Euler angles, and if you find the direct cosine matrix, it is simply a succession of 3 successive rotations. So it's actually a rigid movement. So it's something like this, like that, or like that. So it's not a very smooth movement, it's very rigid, because it's just a succession of 3 separate angles. So I will just explain about gimbal lock. Now suppose the robot is flying at a very high altitude, as you have seen, and we want it to change the altitude very quickly. So we just make it pitch down, and we stop everything. We let it free fall, and then later we try and control it again. So at this part, where the robot is close to its maximum pitch, then there will be a potential for gimbal lock. So that's because if you have the coordinate system something like that, and then when it's turning down, something like this, first, mathematically or programmatically, is you first have this matrix. So when you perform the calculation, this axis will be parallel to the other axis. Then there will be some problems mathematically or programmatically. So that's the problem known as gimbal lock. So for that, we use quaternions to represent orientation and rotations. They have been proved in other branches of computer science and mathematics and graphics that they don't cause gimbal lock. So we describe an orientation about an arbitrarily fixed axis using a 3-dimensional axis and the magnitude of the rotation. So if the robot is oriented by an angle theta about this axis, we can represent the orientation something like this. From that particular quaternion, we can find the matrix which will directly replace the DCM matrix, and this matrix will be gimbal lock free and using quaternions. So that's the reason that why instead of indicating the robot pose like this, we are using quaternions of the form that I have shown. Another advantage of using quaternions is that, as I have mentioned, if we use Euler angles, it gives very rigid movements, but using quaternions, we can specify much smoother maneuvers for the flapping wing flying robot using the concept known as spherical linear interpolation. So spherical linear interpolation, it finds the quaternion representing the smoothest rotation from one orientation to another using the unit hypersphere for the interpolation. So we have one orientation, we have a disturbed orientation, and if we want to recover the original orientation, we can find the smoothest maneuver using this technique. So I will just show one small animation that will make that concept more clear. So let's say this is the original orientation, something like this, and we have a disturbed orientation. So this is the following, what you are about to see is the direct result of using the concept known as slope. It will find a very smooth rotation. So it will give you the matrix representing the smoothest rotation from one orientation to another. Now, so the orientation, the deflection of the control surfaces, as we know, they cause angular accelerations, and Those accelerations we can get directly from the onboard sensors. From those accelerations, we can also find the angular velocities. So for right now, since I have mentioned, in the beginning, we didn't have any mechanism for causing a roll, so that's why this is 0, but we will be changing it later on. So from the angular velocities, we can directly find the orientation in Quaternion format using this relationship. The angular velocity is related to the derivative of the Quaternion using this formula. So the Quaternion representing the orientation can easily be determined using this formulation. And for estimation of aerodynamic forces, so we are not experts in computational fluid dynamics or aerodynamics, so we have decided to adapt more pragmatic ways of estimating the thrust and lift. So thrust is simply power divided by the velocity. The straight line velocity we can easily measure using external sensors, and the power we can also measure. And you might be noting that the single brushless DC motor, it contributes to not only the thrust, but also the lift as well. So if we use all the power available from the motor, it will be incorrect because it also provides power for the lift. So for that, we can easily measure the lift generated by using a load cell. To verify it with the theoretical value for the lift, and this is again from a formula from fluid dynamics, but this time we are using the flap or the velocity of the flapping action, which we have previously calculated. To model disturbance forces, now our aim was to try and create a large-sized robot compared to the current robots, current flapping wing robots that we have, for the only reason that we can use it in a real outdoor environment. Even then, the robot weighs about 400 grams, or 430 actually. Even then, it is still susceptible to disturbances from wind gusts and turbulence in outdoor environments. So for the modeling, MATLAB provides some wind models, but those are all designed to military levels, so it's an over-design to use it. So we model the disturbances just ourselves using Quaternion multiplication. So we model all the disturbances as one single variable, let's say F disturb. And what we do is we can take an external sensor and measure the wind speed. Then based on that, we can create a vector-valued Quaternion-based force vector, where that's the magnitude of the disturbance force, and that will be the Quaternion representing the direction of the disturbance force relative to the initial frame. And that force has been defined relative to the initial frame, so the effective direction that's acting on the robot can directly be obtained through Quaternion multiplication. And again, if we just want to track or describe the motion of the robot center of gravity, we can very easily do it by treating the body as rigid, and we can just use Newtonian mechanics to give us a approximate formulation of the motion of the robot center of gravity. So for experiments, what we did is we simulated basic pitching and yawing movements. So we flew the robot in simulation, and at some point in time, we applied a rudder deflection, and using all the equations, we tried to generate the sensor data in simulation. And we did the same for the pitching motion. We apply a deflection for the elevator, and we do the same. And then we try and do the real experiments. We put the sensor on top of the robot, and then we get the data, and we just compare the data qualitatively. So this is an ongoing project. We haven't measured all the phenomena right now. So I will just show you a video of just what I meant by simulating the robot movement. So something like this. So this is just a simulation showing the motion of the robot, so you don't actually see the wings flapping. But at some point in time, you will see that when the control surface deflection has been applied, then the robot will make a yawing turn, I believe, in this. So all this data has been generated in simulation. This is not real data. So right now, you can see the robot has been making a yawing turn. And in a similar way, for the pitching, where is the pitching? Okay, I was just having one video over here. So for a similar way, we do a pitching test. So first we compare it. So this is the simulated data showing the linear motion of the robot. And the most important part is this green curve. It will show how the robot was flying straight. We apply rudder deflection somewhere around here, and then it yaws to the left, and then it turns. And this is the rotational data. So it gives the angular acceleration, angular velocity, and angular displacement. And you will see that the rotational data, it matches, qualitatively, it matches the real gyro data. And the reason we are using the gyro data to do the matching is because the gyro has got less drift compared to using the accelerometer and to measure the positions. In a similar way, that's the simulated pitching. So the robot was flying at one altitude. We apply the elevator deflection, and the robot changes its altitudes a little bit. And that is the velocity profile at that particular point in time. And then when we get the real data from the gyro sensor, we see something like this. So that was this presentation. And this work is ongoing, so we are going to be doing many more measurements, and which we'll be hoping that we'll be able to present in future conferences.
Thank you very much. Is there any question from the audience?
So right now we have to do some load cells measurements to verify some of our measurements. So for example, lift and thrust, so we have to get that. And also, one of our main core tasks is the implementation of control algorithms. For that one, our expertise is to implement control algorithms, but we are more interested in implementing model-free control. So where you don't need a mathematical model, so you implement control. This one is meant to be a reference for model control, model-based control. So these equations, we will be using it to implement model-based control, which we will be comparing it to model-free control in the future.
Sorry, so in the, you said in the yaw movement simulation,
Yeah.
Okay, we didn't see the finger flapping, but was it pitching up and down or not?
It wasn't pitching up. No, so that was just a simulation of the motion I mentioned. So the wings were not flapping, yes. It was just a simulation of the motion, robot motion. Yes, yeah. But as I mentioned, what we would like to do is to be able to command this robot to fly around a disaster zone, let's say in a circular trajectory or in a figure of 8. So that's what our ultimate aim is. Yeah. And this is all laying the mathematical foundations for that subsequent task. Yeah.
Yes, nice talk, thanks. I would like to ask, what is the advantage of your work over a regular airplane? It can also fly.
That's right, yes, yeah. So as I've mentioned, so flapping wing flying robots are still relatively in its infancy right now. So in the future, when technology matures, when people make contributions, so it's going to be super maneuverable. That's what we hope. Because if you see birds in flight, they can do many amazing things. So right now, it may be an over-ambitious goal, but that's the ultimate goal for the future. Yeah.
You present the using orientation using Quaternion.
That's right.
The equation of motion is still using the Euler angles. Any comment on that?
So yes, Euler angles we are using at the end, output stage. At the output stage, and then we are using it for the motions. But within the processing, inside, we are using Quaternions.
I have a question based on your application.
Yeah.
Do you have an estimate as to what kind of payload it could carry?
Yes.
Also, you said it's to survey disaster zones. So is it supposed, are you planning to put cameras on it? Because the flapping motion seems to be very vibrational, and in order to get still video, would that cause problems? Have you all thought about that?
It would probably will, but we can put small-sized cameras So there are some cameras that are very small we can put, and it will cause some problems, but that remains as a research problem that we have to solve. Yeah.
An estimate for payload?
The gross weight that we have is 430 grams that I mentioned. So that's the maximum that we can have, including the robot. Yeah.
Have you made an estimation of your battery life?
Yeah.
If yes, with what kind of battery?
Yes, so I mean, we can fly for at least 20 minutes if it's fully loaded. So there is a sufficient time, yes. Although after 15 minutes, the flapping reduces, but it can go up till 20 minutes using a 900 milliampere battery.
That's 20 minutes.
Yes. Yeah.
Any more question? Then I would
Thank you
like to
very
thank you for your presentation.